Professor Jaydeb Chakrabarti from SNBOS Center for National Basic Science.
So good afternoon, everybody. I would start with my sincere thanks to the organizers, not only because I got an opportunity to talk before this audience, but also because of the fact that this kind of large gathering has been taking place for last several years, and I sincerely wish that such gathering goes on for many years to come. What we'll be talking about is motion of particles driven through a polymer network. That's the formal title, and the work that shall report here briefly was carried out by Rahul Kormakar, who was a graduate student, and he graduated last year. Right now, he is in chemical engineering department as research scientist, research engineer in IIT Madras. And this particular work was published in Europhysics Letter last year. The whole idea of doing this work came due to the pandemic, and the pandemic actually enforces something: face mask for everybody. And face mask is not only important during pandemic, but also generally, encountering, let's say, the kind of pollution that we encounter in different Indian cities and also in the world. Face mask appears to be one of the first defense that one could use. Now, so far the face mask is concerned, there are a couple of things that people should keep in mind. First of all, the material of face mask. There's a clear guideline by the WHO, namely the mask should have multiple layers, at least 3 layers. The outer layer means the layer which faces the atmosphere, that should be hydrophobic, and the inner layer is which faces our mouth side, which is a polar medium. So it should be a polar material, and in between people, typically what is used as hydrophobic material, like a polymer network made of hydrophobic materials. Another very important thing that I'm sure that all of us actually experienced is the question of breathability. If you have a mask, then breathing becomes somewhat difficult, and as a result, you feel somewhat decongested after some time. The fact is that when you try to breathe some particles, breathe air in, then you put some pressure difference. And as a result of pressure difference, the things actually gushes inside the mouth or inside the nose. And this should be sort of kept as much easy as possible, even if you have a face mask. So what we try to address here, what would be the, let's say, material property that you would be using to design the face mask so that you actually take care of both the scenario into account. So the model that we try to study here is the following. First of all, the mask material which is sort of, fabric materials are essentially, masks are fabric material which are like polymers, and the polymer has got, let's say, so that's a typical example of polymer that we consider, and this has got 2 colors of bits. That means there are 2 types of bits which I'm not going to specify exactly because this specification is not so important. What we do here, as I said, that there's an asymmetric atmosphere in which this mask is acting. So H wall is the indicative of the wall which faces the environment, and P wall that is inside our mouth. H is some indicator of hydrophobic, but we are not really using hydrophobic interaction per se, and P is the polar thing. And this color is in accordance to this thing. So clearly, the H wall has favored, like the black bits, they have favorable interaction with the H wall, and the other gray bits has got favorable interaction with the P wall. So this is how we take this polymer, and first what we do, we create a kind of a polymer melt network. So by melt network, I mean that there are several chains, and the chains are sort of forming a network structure, and it should be as rigid as possible so that it does not break away. So, and then what we do, we take a situation where we assume that the gap between the H wall and the polymeric network is filled up with some particles which we call as the tracer particles. These are of, typically the size that were taken here is of 10 nanometers. And then the particles have got interaction with both the bits. Now the interaction is taken to be simple. The interaction energy parameter is taken to be like, one parameter that tells with the P bits and the other parameter tells with the H bits. On top of that, we take a force acting in the system so that the H wall faces high pressure region and the low wall faces the low pressure region, and we take a force in order to impose this kind of pressure difference. We essentially do via force, which we take to have a linear profile like this. And then the simulation scheme is pretty standard. What we do, we take the entire system, we try to simulate using LAMPS code, and the simulation ensemble is just simple NVT ensemble, but this is a situation where you have a pressure acting on the system. And then the simple calculation that we do, we look at the density profile of tracer particles along the material. First, we talk about the density profile that we encounter if there's no force acting on the system. So without any force, the density profile typically looks like this. Well, one thing I should say that the tracer particles have got favorable interaction with the P walls and not so favorable interaction with the H walls. Now what happens, since you start with the particles at the H wall, so then the particle structure slowly comes into the side of P wall. And this is what essentially the permeation of the particles onto the other side of the wall. And then a typical density profile in absence of any kind of force or pressure difference, the density profile is maximum and then slowly comes in, and then we have the P wall. So what we do, we calculate how many particles are coming towards P wall, and that is given by Q, which is nothing but the integration of the density profile near the P wall peak till the P wall region. And then actually this particle Q is essentially that integral that falls off with the size of the tracer particles, and there's a point at which this number actually goes very close to 0, and that we take as the typical pore size. And then this, what we are interested in is tracer particle size, which is sort of comparable to this tracer size, because the pore size. If the tracer particles are bigger than the pore size, of course, geometrically they will be hindered. But what happens if the tracer particles are less than the pore size, which is a typical case of the viral particles or the droplets containing viral particles are in our mind. So what we do, so since, for this system that we have considered, the tracer size appears to be around 1.8. So now what we do, we take particles, the tracer particles which are less than the pore size. So for example, here what we show that the tracer size 1.5, which is less than the tracer size, and then we apply force, and what we see here, for different temperature, we find that there is an Arrhenius dependence of the P means essentially how many particles are within the network material, and that shows an Arrhenius dependence. So there is clearly a kind of barrier acting on the pressure tracer movement, and this barrier is calculated by you calculating the potential energy of the polar bits and the hydrophobic bits. So basically when a tracer is moving, it encounters interaction with both kind of bits, and what is the energy contribution coming from both interactions. So it turns out the polar interactions are sort of prominent, which is something one would expect. Interestingly, if you suppose you fix this ratio, which is like how much is the polar interaction favorable compared to the other hydrophobic interaction, then if you take a larger particles, then the barrier is higher because that encounters more number of polar particles, and on the other hand, if you increase this strength, that means the polar interaction much more favorable compared to the hydrophobic interaction, that also increases the barrier height. So you see what happens here, that there are several parameters which actually controls the barrier height, and the barrier height is the one which essentially controls the particle movement within the material. So parameters are a lot, like you can change the composition, you can change the bit interactions, you can change the rigidity of the network, you can change the confinement length. So from detailed calculation, we came up with certain values of those parameters where we find that the efficiency, that means the value of Q, is 90% or more. So thank you so much.
Time for questions.
Yeah, this is there.
Interesting talk. So I was wondering, how does this sigma tracer compares to the normal size of the aerosols? Because they are the aerosols which really infect you, right?
Well, aerosols, look, I mean, this is done, everything actually in scaled units, okay? So aerosols are typically of the order of, let's say, it can be as large as a micron, but it starts from about 10 to 50 nanometers and can go till 1 micron. So what we are talking about, this length that I said, are essentially how much is the size compared to the pore size. So you can as well apply this to nanometer or to micrometer, there's no problem. So in the calculation, these numbers do not really matter, what matters is the ratio.
Sorry, what exactly do you mean by this efficiency? I mean, like how do you...
Efficiency means how many particles do not reach the P site. See, basically your effort should be that you stop as much particles as possible. Okay. Sorry. See, basically, you have a certain width, right? Now, if the width is too large, then what happens, the entanglement of the polymer, that becomes loose. As a result, in the pore size increases and it allows everything. And if it's too short, then it's not so easy to synthesize the material, right? So it appears to be an optimum size of the order of 5 micrometer for those combination of parameters. So there's a kind of optimum length so that your network is rigid, so you don't break the network away. In fact, this is where the ratio H versus P becomes important. If P is too large, then the network becomes so cramped that it doesn't allow anything. But then breathability trouble comes in. And if it is too, like if P is too small compared to H, then the network becomes loose. So network is not stable.
So let us thank the speaker again.